Well, here we go, I guess. Hello, everybody, and welcome to the 7th Women for Space conference organized by WIA in Aerospace. Well, it's WIA, but the acronym is Women in Aerospace Europe Barcelona. I'm Monica Llorenç, and I'm another member of WIA, and I will present our speaker for today, who is Estel Cardellach. Thank you, Estelle, for joining us and to be here today. Before starting the presentation, I would like to say that WIA Europe Barcelona is an institution located in Barcelona, but we are also in contact with other groups located in different cities around Europe, as for example, WIA Rome or WIA Berlin, and we are currently doing projects together. Women in Aerospace was founded in the USA in 1985, and in 2009, WIA Europe was founded. WIA Europe is a professional association for women and for men who wants to work and develop professionally in the space sector, to promote the space programs and to support the young generation to come and to contribute in shaping the future. In Barcelona, we are a passionate and enthusiastic group of professional women fighting for visibility in the aerospace world. We hope that the group will get bigger and that we will expand and to consist of other genders soon. It will bring more points of view to the group and different ways to approach the problems. If you would like to hear more about us or about our future projects, you are more than welcome to the end of this year course party, which will take place on Friday, 17th of June at 4 p.m. and it will be online. You can register using the link that we will share on the chat on this presentation, but you can also find it in your social media, for example, on Instagram. That said, our speaker for today is Estel Cardellach. She will explain how we can reuse the signals transmitted by other satellites for different applications. She did a Ph.D. in physics at Politecnica University of Catalunya and a postdoc in USA with NASA, Jet Propulsion Laboratory, and with Harvard University and Institution Center for Astrophysics. She is currently at the Institute of Space Science in Barcelona since 2005. She is the principal researcher of the Spaceborne experiment Radiopolitician and heavy precipitation aboard the Ph.D. low Earth orbiter, and she is a science team member of the recently approached Gnss ESA Scout mission. She is also the local manager of Universitat's Radiopolitician Meteorology Satellite Application Facility. Her career has been focused on developing new science applications or scientific applications of global navigation satellite systems. For remote sensing of Earth, such as the extraction of geophysical information of the Gnss, reflective signals, radio occultation, and geodetic techniques. And that's all. If you have any question, you can write them in the chat and during the presentation, and we will go through them at the end of the speech. Thank you, everybody, for being here. And Estelle, the floor is yours. And guys, enjoy the talk. Thank you.
Thank you. Can you hear me well?
Yes, I can hear you well. Thank you.
Okay, so in that case, I will share my screen. I hope you can see it now.
Yeah, I can see it.
First of all, thank you very much for inviting me to present this type of activities. This is the kind of work I do, and it's related, of course, with the space sector. As the title and as you have explained, I'm going to discuss opportunistic spaceborne Earth observation. First of all, the motivation why we should contribute to a sustained and efficient Earth observation system. Then I will explain what we understand by opportunistic Earth observation. And then I'll focus on one particular type of opportunistic signals, which are the navigation signals. How these navigation signals can contribute to the observing system. And finally, I will focus, I will give examples of GNSS reflectometry applications from space. I don't think I will have time to go through the polarimetric radio occultation section, so I'll stop after the reflectometry section. The motivation. We need to understand forecast, adapt, mitigate, and react to natural and anthropogenic Earth system phenomena. And this requires a challenging Earth observation approach. And this Earth observation should run continuously and in the long term. It should cover the whole globe. It should have fine spatial resolution and temporal resolution. And of course, the data must be of good quality in terms of precision, accuracy, and repeatability. And if possible, this should be sustainable and run at a reasonable cost. And this must respond to scientific challenges. Some of the phenomena, these natural or anthropogenic phenomena, are not fully understood yet. They are not fully modeled yet. And here I list a few examples, like extreme precipitation. It's difficult to study, it's difficult to model, and then it's difficult to forecast. And also we see that the climate models tend to diverge on what is going to happen with extreme events, extreme precipitation events. The same happens with hurricanes and typhoons. They are also difficult to study, and that's partly because of the cloudy and rainy walls. And it's worth noting that despite they have been great improvement in the forecast of the track of the hurricanes, the cyclones, there has been little improvement in the intensity, the forecast of the intensity of these events. Another example would be the atmosphere and ocean interface. This all this it's now being revisited. And oceanographers are realizing that the sub-mesoscale phenomena, these phenomena that are relatively small in size, in amplitude, and in short in time, might have a larger role in the system that was expected. And maybe to close this list of examples, there will be more, of course. It's the wetlands. The wetlands play a key function. They can control some of the greenhouse gases emissions, for instance, for methane, and they are under threat, so we also should monitor them. A key aspect in all these scientific challenges is that there is a lack of appropriate observational data to study them and to improve the knowledge we have about them. And this lack of data comes because of some weaknesses of the current observational system. For instance, the lack of continuity in the scientific spaceborne missions. Now this is getting better because of the Sentinel, the Copernicus program. But most of the purely scientific missions are just operating for a given time, and then they don't have any continuity, any follow-on mission. Also, some instruments and missions are not suited to monitor certain aspects of the phenomena that we are interested in. For instance, in extreme weather phenomena, there are opaque areas, the heavy rain, the hurricane inner walls. And even at microwave frequencies, it's difficult to go through these systems. The same happens with vegetation that blocks the remote sensing, for instance, of water in wetlands. If these wetlands are vegetated, many remote sensing techniques cannot get into the water and get the information. Is it flooded or is not flooded? Tsunamis is also very challenging in terms of remote sensing because the signal is really weak, very small amplitude signals. They are quick and synoptic, really large. So you need to monitor a very large area simultaneously. And finally, for ocean, if we want to better understand the role of the sub-mesoscale, the small systems in the ocean, we need better sampling, both in space and time. And this might not be sufficient at the moment. So with this motivation, now let's see how we define opportunistic Earth observation. It's related to the use of satellites that are not designed for Earth observation. So there are hundreds of satellites orbiting the Earth, and they transmit signals for different purposes, like navigation, communications, broadcast TV, and so. These electromagnetic signals cross the atmosphere and might reflect on the surface of the Earth. And we will call opportunistic Earth observation to the reuse of these signals to infer information about the Earth system, about the atmosphere, the ocean, the cryosphere, the land properties. And the two main techniques are the reflectometry and the radiooccultation. Reflectometry is when signals bound off the Earth and then are collected by a dedicated receiver. This is a bistatic radar configuration, and we can infer information of the surface properties. On the other hand, radiooccultations occur when signals propagate through the atmosphere, interact with it, and a receiver collects these signals and invert the information on some of the atmospheric properties. We distinguish two main sources of opportunity. First of all, the navigation satellites called Global Navigation Satellite System, GNSS, like GPS, the European Galileo system, the Russian GLONASS, and the Chinese Beidou. Also, the regional and augmentation navigation systems. These systems transmit a L-band in circular polarization, but they are weak and usually narrow bandwidth. But the good point is that they do transmit publicly available code modulations. So it's easy for us to receive these signals and use them. The Earth observation with GNSS is a relatively mature technique at the moment. On the other side, we could pack all the rest of satellites that transmit signals, and we call them other sources of opportunity. That could be communications, but yeah, whatever we can think of that transmits signals. Unlike GNSS, they transmit at different frequency bands, radio and microwave. They might transmit relatively high power over certain areas. Some of them broad bandwidth. But in many cases, it's not a public or well-known content of the signal. So not a publicly available codes, for instance, like in GNSS. This field is what we call other sources of opportunity is just emerging. It's quite immature. For this reason, I'm just going to give one example, the only mission that is being developed at the moment that use this technique with other signals of opportunity, communication signals. And then the rest of the talk will be focused based on navigation satellite signals. So this only the single example that I can give, because it's the only one that exists on a Spaceborne mission based on other sources of opportunity, is a NASA mission, a demonstration mission called Snoopy, Signals of Opportunity P-band Investigation. It will operate, it's a CubeSat, very small. It will operate at 2 P-band channels and something around 255 megahertz and 370 megahertz. Essentially, the signals transmitted by the MUOS constellation will be received by these Snoopy satellites, both the direct link and also the reflected radio link. And because it's a relatively long wave, low frequency, long wavelength, it penetrates quite a lot into the soil in particular, and also through the vegetation. And I believe it will be, if successful, the only mission that from space can take direct measurements of the soil moisture below, let's say, 10 centimeters deep into the soil. At the moment, you can find root zone or deep soil moisture products from other satellites, but I believe, if I'm well informed, I would say that all of them come from some kind of extrapolation or fusion with other data, but not direct measurements of what's going on down deep into the soil. It's expected to be launched either last of this year, end of this year, or maybe next year, I'm not sure. So how the GNSS can contribute to the observing system? Here I'm going to review all in general terms. One very positive thing is that these signals are quasi-permanent. That means that they are transmitted not now just for a few years, but they belong to long-term programs. They are big agencies behind that will keep these satellites, will maintain the system running for decades. In that term is quasi-permanent. Also, a GNSS-based sensor does not need to transmit any signal, as we already said. We use the signals transmitted by GNSS constellation. So in that term, it's a passive instrument. Doesn't need to transmit, it's passive. That means that can be smaller, can be cheaper. And if it's small and cheap, you can put it in small platforms, even CubeSats. And that also means that it's affordable to think of constellations of these satellites. If you have a constellation, then you increase the spatiotemporal sampling at a reasonable cost. Otherwise, you cannot do it with a big, costful satellite. As we already mentioned, L-band, it's the kind of band that operates GNSS. It penetrates all weather systems, also hurricane walls, for instance, and it also penetrates some vegetation canopies. For instance, over wetland, that can be very interesting. In green, I marked the good things, the good points, strong points of GNSS for Earth observation. And in red, now I'm going to mention the bad ones. It has low SNR, and the bandwidth tend to be narrow, and that's not optimized for remote sensing. But for some applications, the observable we are interested in is the precise measurement of time, delays, ranges. And in that sense, it's self-calibrated. It's not like a radiometric measurement where you need to calibrate the power. So that can be a very positive thing, and it's been demonstrated to be a very strong point for atmospheric monitoring. So how GNSS can contribute to the observing system? We have several options. The first one was, in fact, just using GNSS for positioning from ground-based stations. And it was used for geodesy, just keeping track of very precise measurement time series, the surface of the Earth, the motion of these surfaces, crustal dynamics and tectonic motion were monitored. In that case, the ionospheric effects and the neutral atmospheric effects were a source of noise, was a source of undesired effects. And at some point, it was reversed. At some point, it was possible to start using these measurements to infer ionospheric and neutral atmospheric properties. Later on, in fact, much more recently, it was seen that these antennas collect multipath from the nearby environment, in particular from the soil, the ground around the geodesy station. And it was discovered that treating this multipath, or looking at this multipath, you can infer properties of the soil moisture, the snow coverage, the vegetation coverage. And if it's located by the sea or by a lake, you can also get the water level. And here we have an example that's from Western US, the University of Colorado. They use all the existing geodesy network of stations to get this kind of products. For instance, the snow depth, the vegetation indexes, the soil moisture. So was a completely opportunistic approach, because the stations were there for geodesy, the signals were transmitted for navigation, and they could get all these other geophysical parameters out of it. Another option is to put a receiver with an antenna and a receiver flying on an aircraft or a low Earth orbit, and put an antenna looking to the horizon, to the limb of the Earth, and collecting the signals of the GNSS transmitters when they set below the horizon. In this geometry, because of the gradients, vertical gradients of the atmosphere, the propagation is not in a straight line anymore. You have some bending of the rays. And this can be measured very precisely because it has an effect in the Doppler. So through Doppler measurements, you get to the bending of the ray, and then you can invert that to vertical profiles of the atmosphere. And that affects, you can apply these techniques to infer ionospheric vertical profiles and also atmospheric neutral atmosphere vertical profiles, temperature, pressure, and humidity of the troposphere. And finally, you can also locate a receiver looking down, also into a plane or a low Earth orbiter, and collect the signals of these same transmitters, but after they bounce it off the Earth. And then you can get sea ice information, glaciers, polar snow, ocean altimetry, winds and waves, or the soil moisture, snow and vegetation. So it's quite complete. For the rest of the talk, I'm going to focus only on this technique, the reflectometry technique. First of all, I want to do a bit of comparison between the reflectometry and the radiooccultation technique. By the way, the radiooccultation, I'm not sure I said that this is what is called a radiooccultation. And the name comes from the fact that because of the bending, at some point, the transmitter is behind the Earth. So in a straight line propagation, you wouldn't see it anymore. But because of the bending, you still can see these signals. The geometries, as we said, the reflectometry, the signals are received after they bounce off the Earth. This is a bistatic radar. There is a transmitter, the bouncing, and the receiver here. So that's the bistatic configuration of the radar. So we get information about the surface, and we prefer to call it multistatic. Why? Because from one single receiver here, you can get not only one reflected signal, but as many as GNSS transmitters you have inside. So you can get simultaneously information from all these different areas that I shown here in red, in yellow. The geometry for radiooccultation, as I said, is quite different. Here we don't have reflected signals in principle. It's a propagation effect. If this is the GPS or the GNSS satellite, we have a receiver in a lower orbit. And as it goes down, as the satellite sets behind the Earth, the rays bend more and more because the gradients change in the atmosphere. And we can here infer the vertical structure of the atmosphere. As I said, these techniques are quite mature, but the reflectometry one is not as mature as the radiooccultation one. Before 2014, we did not have a proper mission into space, just a few samples now and then collected from space. In 2014, there was the UK TDS-1 satellite launch with a payload that had GNSS-R capabilities. That was very useful to start demonstration many applications. In 2016, NASA launched the Cygnus constellation. This is 8 CubeSats that carry all of them only this kind of payload, only GNSS-R payloads. More recently, China has launched 2 LEOs with GNSS-R payloads. And last year, the first few commercial GNSS-R CubeSats were launched by the Spire Global company. On the other side, the radiooccultation technique is now very mature. The first demonstrator was launched in '95. It was called GPS MET. And since then, there have been many other satellites orbiting with this technique, including constellations, the Cosmic Constellation, and now the Cosmic 2 constellation. There are also operational RO payloads designed to be operational for meteorology. And there is also something new, which is the polarimetric concept, which is exactly the same, but collecting signals at 2 polarizations. I will not have time to explain that. It was at the end of this talk, but I'm afraid it would be too long. This was launched in the proof of concept was launched in 2018 aboard the Spanish PATH satellite, and this is something that I've been working since the beginning. The sampling both have very good sampling. In terms of reflectometry, it's quite clear that if it's a multi-static concept and from a single receiver, you can get many different reflected spots. You can see here 24 hours sampling from the Cygnus constellation. It's quite impressive. And in terms of radio occultation, the good point is that this kind of information, vertical profiles of thermodynamic properties of the atmosphere, before the radio occultations existed, the only way to get them were through radio zones. These are these small balloons that you launch with sensors, and these sensors fly up into the sky, and then you lost them. And you have to launch them every 8 hours or 6 hours, and you lost them every time. And this is only done in populated areas or in vessels, so you cannot have this global coverage. And that was very important for the weather forecast. So now I'll focus on reflectometry. And first of all, the measurement concept in a nutshell, in just one slide. As I already said, this is a bistatic radar approach. Unlike most of the radars that are used for Earth observation, this one is in forward scattering in the specular direction, while most of the radars like SAR, radars altimeters, they work in backward scattering, monostatic configuration. And then how we get the information out of this? The main observable we get is what is called the delay and Doppler map, delay Doppler map, or DDM. This is a measurement of the spread of the signal after the reflection. What happens to the signal because of the status of the surface? This is an example of delay Doppler map. We have the Doppler, the frequency delay, the frequency axis and the delay axis here. And that would be a sketch of the surface itself, in that case, the ocean surface with this roughness. If the surface is not rough, if it's flat, like a mirror, that happens sometimes, what we would get is just signal coming from around the specular point, the first Fresnel zone. And this is something that you can imagine that happens when you see the reflection of the moon or the reflection of the sun in a pond, in a lake, when it's very calm. You can see the moon, you can see the sun, this specular image. But when it starts blowing the wind, when this surface gets rougher, you cannot see the moon image anymore, or the sun image. What you see is a set of bright spots that scatter around the specular point. That's what we call the glistening zone. And because of the geometry, these other glistening points, the points that are returning power, scattering power, they have different delays, here sketched in white, and different Dopplers, here sketched in red. So when you map all these power in terms of these delays and this Doppler, what you get is this kind of shapes. This is the typical shape for rough surfaces like the ocean, diffuse scattering. If we focus, if we observe, or we are interested only in the delay, in the time of arrival of this echo, what we can do is range measurements, and we can think of altimetric measurements. Where is this surface vertically? Is higher up or higher down? This will move in delay all this shape. And we can also, well, for the total power that's linked to the electric properties of the surface and also the roughness effects. And we also can look at polarimetric response, which again is a matter of the electric properties and some roughness effects like the structures of the vegetation, for instance. And looking at all these observables, the delay Doppler map, the ranges, the total power, and depending on which surface the signals are reflected off, we can get all these different set of applications: altimetry in the ocean, winds and waves in the ocean, sea ice properties, ice sheets properties, permafrost, soil moisture, vegetation, wetlands, lakes, and so on. And now I'll try to go through some of them. at very high level, I will not get into the details of the retrieval algorithms or just the basics of the principles. I hope it's easy to follow and it's attractive to you. So to begin with, Spaceborne Altimetry. I must say that ocean altimetry is one of the most challenging GNSS applications because the user requirements are very demanding, because the other solutions, remote sensing solutions for ocean altimetry are really good. The radar altimeters are really good. The LiDAR altimeters are really good. They mostly have issues with the sampling. If you want to increase the sampling, if you want to sample these small scale features that evolve quickly in time, that's the kind of problems, but not the measurement itself. It's very good. So competing with these systems, with these radar and LiDAR altimeters, that's very challenging. So the measurement principle is easy, is the delay of the reflected signal with respect to the direct one or with respect to reference. And this delay relates to the vertical location of the reflecting surface. But as we just saw 2 slides ago, the ocean scattering is diffuse. And that means that it becomes even weaker and incoherent. One of the problems then is that we cannot track the carrier phase, the electromagnetic field as it comes. It cannot be locked, just sufficient to be able to extract the power, let's say, during a few milliseconds and then average for 1 second, for instance. And that means that these delay measurements must be done based on the group delay, on this shape of the DDM, how it moves, how it shifts in delay. That's what we call the group delay measurement. And if you want to have good precision, range precision using group delay, you need relatively broad transmitted bandwidth. That's what the radar altimeters do. They can transmit quite broad bandwidths. So they have, in the time domain, they have a ramp away from that ramps up very quickly. This is not the case, unfortunately, for GNSS. We have relatively narrow bandwidths. So we would need to do a competitive group delay altimetry with GNSS. We would need that the GPS, the GNSS satellites transmitted broader codes. At the moment, they are not sufficiently broad to make this technique competitive using the group delay. And we have here an example from TDS-1 satellite. That's the solution using TDS-1 reflectometry satellite, and that's the comparison with the DTU-10 mean sea surface level. And we can see that they correlate pretty well, but still we are talking of errors between 3 and 7 meters, which is not competitive compared to radar altimeters and LiDAR altimeters. But what happens when the reflection is not diffuse like in the ocean, but if the reflection happens over a smooth surface, then it's possible to track the phase of this electromagnetic field. And every time this electromagnetic field spins 1 cycle, this is only 1 wavelength of change in the range. And for GPS, 1 wavelength is approximately 20 centimeters. So if we can track the phase, that means that we can sample this wavelength, we can subsample it. That brings the precision to a much better standards. And that's what happens over the sea ice. Over the sea ice, the surface is smooth enough, the carrier phase can be tracked, and then we can get very precise range measurements that translate into very precise altimetric measurements. And for instance, we have here 3 examples from these references. They were done using TDS-1 satellite data. In that case was over Hudson Bay when it was frozen with sea ice. And these 2 examples are around Antarctica in the Southern Ocean, also over sea ice. And we can see that each point, blue point here and gray point here, it's a 20 millisecond solution without any further filtering or smoothing. And we can compare with the thick lines that are the mean sea level. And we see that the correlation is quite good. Of course, there are effects like tides, maybe atmospheric effects we have not corrected here, but it's clear that in terms of precision, we are getting very good precision of the order of a few centimeters in very high sampling, 50 Hertz sampling. Unfortunately, over the ocean, we cannot get this in general because the scattering is diffuse. They are the waves, the roughness. But there is an exception, or there is a condition that boosts the coherence of the scattering, which is a particular geometry, the grazing angle geometry. If we collect these reflected signals not when we are just above the surface, but when we collect them after a slant reflection, then the effective roughness is much smoother. And we have tested this idea using Cygnus data in grazing angle near the coastal areas. And we got, for calm conditions, up to 6 meters per second and above 1 meter of significant waves. We got also similar precisions, 3 to 4 centimeters at 20 Hertz sampling. And we can see here an example in the Caribbean. Again, in blue, that's the GNSS are solutions every 50 milliseconds in that case. And here the same, and then in red, the mean sea level. And we can see that the noise level is very low. The precision hits 16 centimeters at 20 Hertz, and this is 9 centimeters at 20 Hertz. So that was for altimetry. And let's now have a look at the scatterometry. Scatterometry is the measurement of the roughness itself in this context. It's a measurement based on the power received and the deformation of this delayed Doppler map. And over the ocean, the geophysical parameters that drive this are the wind and the waves. Sorry. This works even under thick clouds and heavy rain, so it's suitable to study the wind structure even in tropical cyclones, hurricanes, and typhoons. And here we have a couple, we have an example of the ocean winds obtained from TDS-1. I think that was the first paper that used the TDS-1 to retrieve the wind speed over the oceans. When compared to ASCAT, the scatterometer aboard the EUMETSAT METOP, you can see that the root mean square error is of the order of 2 meters per second, at least at these ranges, up to, let's say, 15 meters per second wind. And then for hurricanes, the performance is a bit more challenging. We still can get winds, but it's more challenging. There is a loss in sensitivity. But still, we can see here an example crossing the Trami typhoon in September 2018. The plots I'm showing here correspond to these two tracks crossing the eye of the hurricane. And we can see the two of them are like, I think we're 10 minutes apart or so in a very similar area. And we can see in gray and black the GPS solutions that are above even 40 meters per second, while the ERA 5, this is a reanalysis model, atmospheric model, could not get these high winds in the modeling. And in fact, it has already been proven that it's possible to assimilate, to ingest these data sets, the Cygnus data sets, for the forecast models for cyclones, for hurricane prediction models. And it was seen that compared to the simulation of the conventional set of data, the assimilation of the Cygnus winds is more effective in improving the track forecast. And a simulation of both GNSSR and conventional data shows potential to provide a better representation of all the structure, all the parameters that define the hurricane, the cyclones. On the cryosphere is all the frozen parts of the Earth. And there have been many different applications developed using spaceborne data for cryospheric applications. For instance, sea ice detection has been very successful. There are several, I would say, many different methods published, and all of them report success ratios of the order of 98% with very low false detection rates. Here we have a couple of examples. This is the DDM, this observable for the ocean and for sea ice. So as you can see, it's easy to detect when there is a transition between ocean and sea ice. And in that case, what it was used was the polarimetric ratio. Over the ocean is the polarimetric ratio was little, while over sea ice we have a stronger polarimetric ratio. But there are many other techniques reported in the bibliography. Another thing is the sea ice type classification, not only the presence or no presence detection of sea ice, there is ocean, but what kind of ice it is. Here we have a couple of examples. This is a very early one from 2015, just after the TDS-1 data was released for the first time. In that case, what was done was to combine the information about the total SNR with the information of the decay of this waveform, how fast it decays. And if we plot these two parameters, the SNR and the power decay, what we saw is that some areas correspond to multi-year ice and some others correspond to first-year ice. That was an empirical approach to begin to use this reflectometry data for classification of the sea ice. Here we have a much advanced approach based on artificial intelligence, I think on some sort of neural networks, if I remember correctly. And in that case, they classified according to three different ice types: first-year ice, multi-year ice, and young ice. And we can see here the ground truth corresponding to the tracks of the GNSS, and how they compare pretty well. In fact, they reported percentages of successful classification between 70 and 82% success. And as you see, the misclassification values were relatively low. The highest one was nearly 12% in this particular case, but for the rest was quite all right. Another thing that is being done is the sea ice concentration, how much sea ice you have in a given area. And that was done also through artificial intelligence. The sea ice concentration absolute error was below 9%, and the correlation coefficient with the reference or ground truth data was above 0.9, so very good. In that case, they converted the delayed Doppler maps that we represent them as matrices into a linear arrays. So each column here would be one DDM converted, reshaped into a vector from a matrix to a vector. And then over this time series of DDMs in the form of vectors, they would apply these artificial intelligence algorithms. And we have here an example of the estimated sea ice concentration and how it compares to the ground truth concentration. And we can see that indeed the correlation is very high. For sea ice thickness, a possible way to measure the sea ice thickness is through the precise altimetric measurements, which is what is done, for instance, for Cryosat 2, or the radar altimeter. Unlike the radar altimeters, and because this is L-band instead of higher frequency bands, we have the suspect, it's an hypothesis, that the main reflection, what we are measuring, is not the top of the ice, the altimetry of the top of the ice, but the bottom of the ice, the interface between the ice and the water beneath. And okay, that was our conclusion after analyzing several tracks. I plotted here 3, but we have several more tracks. And in most of them, or on all of them, what we notice is that the GPS solution here in blue was below the mean sea surface level. And it was deeper below as the ground truth for sea ice was higher. So that's the sea ice thickness from, I believe it's from SMOS retrievals, the SMOS satellite mission. And as you can see, as SMOS said that the ice was getting thicker, our solution, our residual, was getting much below. It correlated very well, and we find this in many different tracks. But this is to be confirmed. So this is an hypothesis. We have several, quite a lot of tracks that fulfill this, but it's something that we have to confirm. For the ice sheets, that ice sheets are the bodies of land in the poles, like Greenland and Antarctica, we can also do altimetry. They are covered with a very thick layer of ice, and we can do altimetry. We have an example here, 2 tracks from TDS-1 over Greenland, and we have here exactly the same, but repeated over the Antarctica, compiling a lot of TDS-1 data, reflectometry data over Antarctica. And this is how it compares with Cryosat-2, which is a radar altimeter. And as we can see, the comparison is quite good. Another thing that can be done with reflectometry is the melting fraction in these polar sheets. Here we have an example for Greenland using TDS-1 data and comparing the variation in the reflectivity of these reflected signals from one season to the other, from 1 month to the other. It's seen that this increase in reflectivity is linked to the melting of the top layer of the ice sheet. And what we see here is the number of melting days in Greenland, according to independent sources, and this variation in the reflectivity that we see in reflected GPS signals. For permafrost, the active layer, so that's the soil that gets frozen, and the active layer is the top part of this, the top layer of the soil that is not permanently frozen, but it changes. It freezes and then it thaws, it melts. And that changed the permittivity of the surface, and that was monitored using the SNR differences, the increase in SNR between different seasons. And we can see here using GPS reflected signals and how it correlates with the SMAP level 4 soil temperature maps for the same period. Okay, with that we move to land applications, soil moisture. Soil moisture is also a very successful application. Very good results have been obtained by different groups using different approaches. Many of them use also artificial intelligence, and I just selected 3 of them here for you. In that case, the Cygnus base, so GNSS-R-based soil moisture is compared to ISMN soil moisture with very good correlation. In this other case, again, we compare the Cygnus soil moisture retrievals with the SMAP soil moisture retrievals with also very good correlation. And here, another approach using a different technique, all of them based on GNSS-R using Cygnus. And this is how it compares 1 day of Cygnus retrievals with the 1 day of a SMAP retrievals, the same day. And the same here for 3 days, accumulating 3 days with Cygnus and accumulating 3 days for SMAP. And you can see again that there are very good correlations. The results are quite consistent. For vegetation, I only have one slide for vegetation. This is not as studied as soil moisture, but there are some promising results. Most of them use artificial intelligence algorithms, and also they make use of ancillary data because everything cannot be resolved at once. It's too degenerate, it's ill-posed problem. So you need ancillary data for this. And here we have this example where the Cygnus retrieval, GNSS-R retrievals here and here are compared to the ground truth from the geocarbon above ground biomass catalog. We see that the big picture, the correlations are quite good. If we go to the detail, we see here, I believe this is the African, Central African forests. That's for geocarbon and that's for Cygnus. We see very well the same structures and nearly similar values. Maybe here we see a higher above ground biomass values than the ones provided by GNSS, but in general, there is a good agreement. And the same here for the Amazon basin, all the Amazon area forest. We can see also here good correlations. And that's the same GNSS-R and the reference data for Eastern US.
Sorry to intervene. 5 minutes left, more or less. So
yeah, perfect. Yeah, I think that's what I will need.
Okay.
A spaceborne, wetland, and flooding information. As we said, L-band penetrates the vegetation, and that makes possible to detect what's going on under this vegetation. And we have high sensitivity to water, especially in calm water, because then it has a very coherent, very high coherent response with very strong echo. So all these things considered, several groups have worked in ways to detect flooding, to detect the water and the vegetation in forested areas. And that's, I believe this is part of the Amazon basin in what is Pacamaya, Samiria. I believe it's there, yeah. That's for pulsar detection, and that's for the GNSS-R detection during the same periods, 2 different periods. And in that case, the categories were open water, flooded vegetation, and non-flooded areas. And if we use the carrier phase, it's even better, because then GNSS goes through the vegetation, but of course the vegetation attenuates the signal. So if we use the reflectivity, even if it's flooded and you have very thick vegetation, then it's difficult to guess whether there is water or not. But if you look at the phase and you get coherent scattering, as it happens when there is water underneath the vegetation, then you get a lot of coherence, as it's the phase coherence in red, and in blue when there is no coherence. So that would be flooded and no flooded. Even when it's extremely vegetated with a lot of biomass above the water. And to conclude, the status of the missions, which missions are currently orbiting. After the decommissioning of the UK TDS-1, now there is only NASA, the Cygnus 8 CubeSat constellation, that are providing data in a public way. But it's not the only system orbiting with GNSS-R. There's the China's Bufeng 1A and B, so 2 satellites with GNSS-R payloads. It was launched in 2018, but I believe the data is not available yet to the public. There is the Spire Global constellation that now I think it has 4 CubeSats with GNSS-R payloads. And ESA if FSCAT 2 6 units CubeSat, one of them carrying GNSS-R. So in total, now we have 15 GNSS-R satellites, and there will be 3 more GNSS-R payloads orbiting soon. An ESA small mission, a Taiwanese LEO, and a Chinese operational meteorological series of satellites. So this can be a long-term program for GNSS-R. There is also an a Gnss scout mission that was just approved a few months ago. It's called Hydra Gnss. The phase B to E studies are starting this August. It's a GNSS-R mission. We don't know yet if it's 1 or 2 satellites in polar orbit to sense soil moisture, inundation, freeze thaw, and biomass. It's quite unique in several aspects. It has dual circular polarization that will help distinguishing vegetation from roughness effects. There will be a coherent channel, so we will get carrier phase information continuously, not only, so far it was only in dedicated moments that these missions could get raw data, and this will be in a continuous mode. It will be multi-GNSS for GPS and Galileo, and dual frequency. All these are quite new features of this mission. It will complement a SMOS and a SMAP, biomass, and some of the Sentinel satellites. So to conclude, there is a need of Earth observation data to help both understanding some phenomena and the long-term monitoring of essential climate variables in a sustained way. And GNSS signals can contribute, enabling low-cost, passive, and self-calibrated measurements. They enable constellation-like approaches, and that would increase coverage, time-scale resolution, and the feasibility of long-term operations. It's sustainable, it's feasible to, yeah?
Sorry to intervene. I know you're in the conclusion, but they are telling me in 1 minute, maybe it's closed, the connection.
Oh, really?
Yeah.
Okay, I'm sorry.
Sorry for that, we didn't know. So, so thank you. Just in case, I don't want to stop without question. I don't know if we will have time to do questions. So in case it stops for people that are attending this meeting, then they will have your presentation, I guess. Or they will have the video, sorry, they will have this video. They can put the questions afterwards so that you can answer. And thank you very much for being with us. It has been a pleasure to have you here. And so, sorry, we didn't know it was stopping in at 7. So
okay.
So thank you. So well,
I don't know what's the time. Sorry. So
yeah, it's 7. So they told me at 7 it will probably stop the Zoom.
Okay.
We don't know 100%, but 99% they told me it will stop. So thanks. This was a very good presentation for the people. The presentation will be, we will put in the through the WIA, I think Instagram, the link and the website. So you will, people that are asking whether they will have it, they will have access to this. Okay.
Okay. I'm sorry that I was so slow.
No problem.
So yeah, it was not your problem. It's just that we reserved the Zoom on until 7 o'clock, but maybe we can continue, and it's only closing in case that someone did the same reservation at 7 o'clock. I don't know exactly how it works, but maybe if it's free, we can still alive. I'm not sure. I'm saying that because it's 1 minute past 7, and we're still talking, and the Zoom is still alive. So it's up to you if you prefer to continue, and if it's handing later, pues. I don't know what you would prefer to do. If you want to do some questions, or you prefer to finish here?
It's a question to me. To me, it doesn't matter. So
yes, yeah, so it seems that our pronostics were wrong. So the Zoom is continuing. So what I proposed, so you were doing the conclusions. If you want to conclude your presentation, and I will just then take the advantage to do some, or I go directly to the questions that we have for you.
I think it's okay, because at the end, the conclusions are very repetitive of things I already said.
So now that Zoom has given us this opportunity of a few more minutes, so let me, I will put my camera. Let me ask you some questions. So here there were some comments, for example, saying L-band can also give some subsurface info.
That's correct, yes.
Knows about it, yes. And grass on Metop. Someone put this comment.
That probably was a comment on radiocultation, but now I don't know exactly where it would apply.
Okay, and then I would like to know, so for someone that would like to work with you or something, so is it possible to be able to work, do you have any open position, or do you have something that people that are seeing us, if they want to join you or whatever?
Yeah, I think if people, we tend to have problems to find students for PhD student fellowships, for instance. Sometimes we do have the money and it's difficult to find people. So I would recommend that they contact us. They will find my email in the ICE CSIC.es webpage. And yeah, they can send me the CV. At the moment, we are looking for students for a JAE intro, internal CSIC fundings for 6 months. I think it's for master students that want to apply for a PhD and they don't know if the PhD fellowship will go forward. So it's kind of testing time, waiting for the final PhD contract, PhD grant. So if anyone interested in, and at the moment in doing a master degree or enrolling into a master degree next year, they can contact me and we can discuss this. And then also we'll have money related to Hydro GNSS mission. So I think a PhD student to investigate all the new aspects of the Hydro GNSS features, the coherent channel, the fact that we'll get data in phase and amplitude, the carrier phase continuously, and the polarimetric aspect. So there are a lot of new things that could cover a PhD thesis.
I think it's important information for the people that is looking this presentation. And well, to finish, do you have any message that you would pass to the new generations, of people that want to study this, mainly women, but not only women, but also men? So any recommendation, any from an expert like you?
Yeah, to me, the recommendation would be to open up their minds and be aware that the space sector is multidisciplinary, very transversal to different disciplines. And I think it's going to keep not only continue being multidisciplinary, but probably will be even more. So it's an opportunity to keep busy with interesting things and not getting bored. Yeah. So yeah, the message is open your mind and try to see the big picture.
Thank you. And well, before closing, I have one last comment. I think it's important to read it. So it's someone that says, "Hi everyone, I'm aerospace engineer student from India. How can I stay in contact? I'm going for masters this year." So I will.
Yeah, I think I can post here my email and then
great.
And with this email, they can
you put it in the chat. Okay, and we will put it also in the article when we will mention your presentation. If you agree, we will also put your contact email so that people can contact you.
Yeah, if possible, in a way that is not easy to then get into all these spamming companies. I don't know if that's possible.
Okay, so Estelle, thank you very much. Thanks for your time. Thanks for this great presentation.
Thank you for the invitation and apologies for being slow and
no problem. There is a lot of knowledge in your head, a lot of things to share with us, so we really appreciate that.
Thank you
very much. And thank you everybody. Thank you the people that have joined this meeting, and looking forward to seeing you in the next one. And I think the next one is the party, let's say the final event of WIA that we will have next week, where we will explain what is planned for next year, and we will also make a summary of all the activities of this year. So thank you everybody. Thank you, Estelle, and see you soon. Bye-bye.